Hey, here's some physics problems. This is chapter 10, numbers 59 through 65, odd. Let's see, number 59, we've got a crankshaft that delivers energy from the engine to the axle at the rate of 100 horsepower, which is 74.6 kilowatts, or 74,600 watts. That's power, right? And when rotating at a speed of 1,800 revolutions per minute. What torque does the crankshaft deliver? All right, so let's see. We have we want to know about torque, and we have power and angular velocity. You might remember that back in the non-rotational world of things, power is equal to force times velocity. So the relation, analogous relationship for rotational stuff would be force would become torque, and velocity would become angular velocity. So if we want to find the torque, I think we have this, so we're in good shape. We just need to change this to radians per second. So let's see, 1 revolution is 2 pi radians, and 1 minute is 60 seconds. So I need to multiply by 2 pi, divide by 60. Multiply by 2 pi, divide by 60. That gives me about 190 radians per second. That's my angular velocity. Right? So if I want to know the torque, then I have power, 74,600 watts, is equal to torque times angular velocity. And let's see, that's 74,600 divided by 190. It's about 390 foot-pound. Sorry, that's our standard unit. 390 Newton meters of torque. If you've ever seen in the world of automobiles, the people do talk about torque. The standard unit, if you think about what would the unit of force be, not the SI unit, but our unit. Our unit of force is the pound, and our similar unit of distance would be the foot. So you hear people sometimes talk about foot-pounds of torque. That's just different than Newton meters, right? Same idea. All right. Number 61. 61, we have a 32 kilogram wheel, which is essentially a hoop. That means its moment of inertia is just mr squared, with a radius of 1.2 meters. It's rotating at 280 revolutions per minute. It must be brought to a stop in 15 seconds. How much work must be done to stop it? And what's the required average power? There's a couple ways to approach this. I looked at this problem with a few people. You could do some kinematics stuff and come at it that way. But I'm not going to do that. I'm going to think about work in terms of energy. I know that work is equal to change in kinetic energy, right? The net work done on something. So, in other words, if this wheel has so much kinetic energy, then the amount of work it would take to stop it is exactly equal to changing its kinetic energy to 0. So it would be the negative version of however much kinetic energy it has. If you think about work as the mechanism by which energy is transferred into or out of a system, then we just need to get all that energy out, all that kinetic energy out. So that's what I'm going to do. I'm just going to find the kinetic energy and do it that way. So the kinetic energy of the hoop is equal to 1/2 I omega squared. I've got the omega, but the units are wrong. I just did that conversion here, so converting that 280 times 2 pi divided by 60, that's about 29 radians per second. And the I, the mr squared, would be, let's see, m 32 times r squared. That's about 46 times omega squared. That's going to be the kinetic energy of this. 1/2 times 46 times 29 squared, so about 19,000 joules. So the amount of work needed to stop it is equal to, just have to take all of that energy out of the system, like so, right? Number 63. This is similar to a problem that we did in class. I think the first example that we did of energy type considerations. So we've got a meter stick held vertically like this, and we want to know how fast, let's see, the speed of the other end of just before it hits the floor, assuming that the end of the floor does not slip. So we'll consider this to be a thin rod rotating about its end, and we've done that calculation before. A rod about its end. The rotational inertia is 1/3 ml squared. And we know that the center of mass is going to go from here to here. So the change in the height of the center of mass is going to be 1/2 meter. It's going to drop by that much. So the conservation of energy equation here would be all the gravitational potential energy it has, because its center of mass is here, is going to turn into the rotational kinetic energy that it has when it hits the floor. Right? So this is mgh is equal to the kinetic energy of rotation, which is 1/2 I 1/3 m times the length of it, it's 1 meter long, squared. That's 1/2 I omega squared. The m's cancel out. These 1/2s cancel out if you want. So it looks like omega squared is equal to, let's see, I'd have to move the 3 over, 3g. Is that it? That's all that's left there, right? So omega is equal to the square root of 3g. Which is 5.42. I think we might have even seen that, depending on which class you were in, which example we did, we might have even seen that number come up. 5.42 radians per second. But that's not what they were asking for. I think they wanted to know how fast the end of the stick's going. And since the end of the stick, I know that V is equal to omega times R. So the end of the stick, well, the end of the stick is actually 1 meter away from the axis. So we just multiply by 1. So it's actually 5.42 meters per second. Oops, lost you there. Right. So those are pretty manageable. 65 is a little bit harder. And they make a recommendation which makes it a pretty interesting calculus problem. So I'm going to approach this one in 2 different ways. I'm going to do it ignoring what they say about the energy considerations, and then I'll go ahead and show you what they're talking about there. All right, so a tall cylindrical chimney falls over with its base. So this is very similar to the meter stick that's falling over. It's just a larger thing. So it's falling, and at the particular instant that we're paying attention here, it makes an angle of 35 degrees with the vertical. So right here, this is 35 degrees. They want to know what's the radial acceleration of the top. Radial means along the direction of the radius. So radial acceleration in this direction, we're talking about centripetal acceleration. That's just another word for that. Radial acceleration in the direction of the radius, that's centripetal acceleration. And I know that that's equal to v squared over r, right? Or, if you want, omega squared r, right? Which, and this might be better for us since we're doing rotational stuff. And then the tangential acceleration that they ask for in part B is alpha times r. So to find the answer for part A, I need to know what omega is, right? And to do that, I am in fact going to do conservation of energy. So it's a little tricky here. If you can imagine when the chimney was here, the center of mass was here, and now it's rotated, and the center of mass has dropped by that distance, right? So the chimney, and we do know that the length of the chimney, or height, whatever you want to call it, is 55 meters, right? And that's all that we know. We don't know the mass of it. Okay, so let's see if I can figure out what that delta H is. So this is a geometry problem that we've seen before. I know that this distance right here, from here to here, that's half of the length of the chimney. That would be 27.5. Right? And then it rotates 35 degrees. And I'm interested in this distance right here, from here to here. So that's 27.5. The delta H that we're looking for, it's 27.5 minus, this also is 27.5, right? It's still the chimney. So that, and this is the cosine part of that, adjacent to the 35-degree angle. So it's 27.5 minus 27.5 cosine 35. Right? That's my delta H. Okay, so my conservation of energy equation, this is all to do part A. The mg delta H is turning into 1/2 I omega squared. And we're treating this thing, again, like a rod, which is a good approximation for it, right? It's a pretty tall, skinny thing, so it would work well. Okay, so m, I don't know. I'm hoping that that will cancel out. G, delta H is this expression, 27.5 minus 27.5 cosine 35 equals 1/2. The moment of inertia of a rod about its end is 1/3 m times the length of it squared times omega squared. And there's my m that I can cancel out. So let's see what we can do here. If I can get this into my calculator without messing it up. So I've got G times 27.5 minus 27.5 cosine of 35. Check my mode. I'm in degree mode. That's good. So over here, on this side I have 1/6 of 55 squared. 55 squared over 6, so that's 504.7 omega squared. So omega is going to equal the square root of 48.74 over 504.7.31 radians per second. Oh. That's what I got there. Now, is that the... No, sorry. We're trying to find the radial acceleration of the top. So the radial acceleration of the top is the centripetal acceleration, which is equal to omega squared r. So I just have to take that number, square it, and multiply by the radius. It's 55. So the radial or centripetal acceleration is 5.32 meters per second per second. Right? That's part A. Part B, there's a couple of ways you can go, and I'm going to go with what I would have done if they hadn't said anything about energy considerations. I would have looked at this rod that's free to rotate about this end. That, okay, where does gravity act? I mean, gravity acts on the whole rod, but it actually works if you hang the gravity vector and consider gravity, all of gravity, the entire gravitational force, to be acting as if the entire object had its mass concentrated at the center of mass. So I'm going to hang that gravity vector right here at the center. And for the purposes of torque calculation, that's where it's acting. So that means it's acting at a distance of half the length, right? So the torque being caused by gravity is equal to the gravitational force times the radius, L over 2, times the sine of the angle between them. The angle between them here, it's not actually the 35, it's really this is the angle between them. When you say the angle between two vectors, it's like the two vectors are the hands of a clock. They're coming from the same point like they would in a free body diagram. But the sine of 35 and the sine of 145 degrees are actually the same. Right? You can think about the unit circle and convince yourself that that's true. So you can use the 35-degree angle. It works. It's either angle between them will give you the same sine value. All right, so that's how I find the torque. And then I know that since net torque, and this is the only torque, is equal to I alpha. That's Newton's second law in rotational form. So my angular acceleration is equal to I over... did I find this yet? I guess I did here, but I didn't really do it. So I guess I better write this out too, because I have the m that needs to cancel. So let me write out the equation. Let's do that again. So I'm going to write out my equation. Here's my torque. Length is 55 times the sine 35 is equal to I, which is 1/3 m L squared, my canceling m's, times alpha. You see that all? Just about. So if I'm trying to solve for alpha here, also if you wanted to, you could cancel one of the 55's cancels. So I've got g over 2 times the sine of 35 times 3 divided by 55. So I got 0.1, if I did that right, 0.153 radians per second per second. Now, that's one way to do that. And let's go ahead and do part C, assuming that we had done it this way. So at what angle is the tangential acceleration equal to g? The tangential acceleration, oh, did we find this? No, we didn't, did we? That's the angular acceleration. To find the tangential acceleration, that's a times r. So let me multiply that by the radius. So that's equal to 8.43 meters per second squared. That's the actual answer for that part. And then they want to know what would the angle have to be to make this equal to the acceleration of gravity? Well, nothing would change in this whole expression here except for this, right? So if I took this whole expression and the angular acceleration, the radius is still going to be the same. So if I want the tangential acceleration to be 9.8, this is part C now, then my angular acceleration would have to be whatever 9.8 over 55 is, about 0.178 radians per second. That's the angular acceleration that would result in having a tangential acceleration of 9.8. So then I could go back to this equation here, where everything would be the same. I would have my m's would still cancel out, those 55s would still cancel out. I'd have still, just copying this here, g over 2 times the sine of that special angle I'm looking for is equal to 1/3, one of the 55s cancel, times 55 times 1.78. So sine of my special angle would be, let's see, 1/3 times 55 times 0.178. G over 2 is 4.9, so divided by 4.9. I think that would be it. So 0.66, looks like about 2/3, 0.666. The trigonometric value of the beast. And then if I take the sine inverse of that, that is an angle of about 41.75, 76, 41.8 degrees, just about. Right? Now, real quick, I want to show you something really cool that they did. They said they expected you to do this not using torque, which we just did, right? And we did this using hanging that force value, or that force on the center of mass there. Here's the radius it's acting at. We did torque, Newton's second law in rotational form. So we definitely used torque there. And their suggestion in the book was, don't use torque. So let me show you how they did that, because it's just interesting. You wouldn't have to do it this way, but it's very cool the way it works, and it uses some nice calculus that we know how to do. So going back to part A, where we had mg delta h is equal to 1/2 I omega squared. Going back to that. Remember this expression right here? This was mg times L over 2 times 1 minus cosine theta. If you wanted to do it for any angle, this is how it would have worked out. That's like L over 2 minus L over 2 cosine theta. You can go back to our drawing and look at that if you want. But that is how much, if it rotates down through an angle theta, that's how much height the center of mass is going to give up. Maybe I should put that there, just to remind us of that. This thing is a thin rod. We're treating it as such anyway. So I would have that 1/2 ml squared times omega squared. So this is a general expression, not for that 35-degree angle in particular, but for any angle theta, right? Now I'm going to take this expression and we'll clean it up a little bit. The m's cancel out. These 1/2s can cancel out. One of the l's can cancel out. So if I saw this for omega squared, I would end up with this 3 would come up top here, 3g, and then on the bottom I would have an L. I think I'm good there, times the quantity 1 minus cosine theta. All right, I think that looks good. Now, what they did here, this is the move, the tricky move that you might not think of. They took the derivative of this equation with respect to time, which is very much like a related rates problem, right? They're going to take the derivative of this equation with respect to time. So let's try that. What's the derivative of omega squared? The derivative of omega squared is 2 omega. But since we're doing like a related rates derivative with respect to time, every variable that I hit, a d, that thing, dt, is going to pop out, right? Just like related rates. Not just like, it's not just like related rates, it is related rates. 3g over L is a constant, times the derivative of this expression. The derivative of 1 is 0. The derivative of negative cosine is positive sine theta. Times, we took the derivative of a variable. This is changing the theta. So the derivative of that would be d theta dt. Now, the cool thing about doing this in physics is that these things actually have other names, right? d omega dt, well, that's angular acceleration. d theta dt, that's angular velocity. So I got an angular velocity here and here. Those cancel out. And I get this equation here, now solving for alpha. Alpha is equal to 3g over 2L times the sine of theta. And that is a cool expression there. That gives me the angular acceleration of this thing as a function of theta. That is pretty cool. And just in case you were wondering whether it was constant or not, you can see clearly here it is not constant. The angular acceleration, when it just starts to tip and the angle is really close to 0, sine of 0 is 0, so the angular acceleration is going to be very small, and then it's going to increase as the angle increases. And that makes sense because as the angle increases, the torque will be acting at a closer and closer to 90 degrees. So it will have more and more effect. So we could check our answer for part here. Remember when we had this, we got 0.153 radians per second. So according to this, we should get 3 times 9.8 divided by 2L would be 110 times the sine of 35. I sure hope that works. No! What did I do? Oh dear, I didn't. Hold on. I should have divided there. There we go. And it did. Gave us the same answer. So that's kind of cool. And then, so they proceeded from here. They never used torque to find this. They did it just by taking the derivative of an expression with angular velocity in it. I thought it was a very clever thing to do. Nice little flexing of the calculus muscles. There you go.